Okay, welcome everyone to the last installment of the GOCC this semester. We're very pleased to have Sheila Sundaram speaking to us today. And before we start, just a quick reminder again of our community statement, which says that we're all learning here and everyone has something to contribute. If you have comments or questions, you can put those in the chat and one of us organizers will unmute ourselves and ask on your behalf if you don't want to ask yourself, or you can ask directly. That's fine also. And last thing is that no one has all the answers, so it's okay to not know things. That's why we're here, we're learning. So we're very pleased to have all of you here and finish the semester with Sheila's talk today. And so let's welcome Sheila, who will be talking about on some positivity problems in algebraic combinatorics. So take it away, Sheila.
Thank you. Thank you very much for the invitation. This is a great colloquium, and I've listened to many amazing talks. So I hope I can say something interesting today. All right, so one thing I wanted to say was in my abstract, I had said something about homology representations, and I realized that that was a little too ambitious. I am not going to get to that part of the talk. So, okay, so this talk is about some work that I did 3-4 years ago, a lot of enumerative things came up. It was mostly algebraic. It came from representation theory, but a lot of enumerative things came up. So I'm hoping to, interest everyone. You don't have to know too much representation theory. I do need to start by just setting some notation about partitions. So I will go ahead and do that. So I'm going to write lambda and the \v' n for a partition of n, right? So for me, this is just a k-tuple of positive integers that add up to n, and its length is the number of parts, right? One of the stars of this talk is going to be the reverse lexicographic order on partitions. So this is, I'm going to write lambda just greater than mu if either lambda1 is greater than mu1, so the first part of lambda is greater than the first part of mu, or the first time a part differs, the part in lambda is bigger than the part in mu. That's basically what this is saying. Okay, so this is a total order on the set of all partitions. The P of n is the partition function. The top element is the partition with a single part n, and the bottom element is the partition with all ones, right? And if you write it like this, I could write it, sometimes I'll write it the other way. You'll see I'm not very consistent, but this way it's easy to see how to go from one to the next, for me anyway. Okay, and I wrote out the values of the partition function there just because I like to see actual numbers. And let's see. So, this is one annoying thing about Zoom is I don't know how to get rid of the thing that says I'm sharing my screen, but okay. So the symmetric group, but I assume you can't see it, right? So the title should say symmetric group and sign representation. All right,
yes,
sign. Okay, all right, so what's the sign of a permutation? Well, it just depends on the cycle type. So I think everybody knows this. There's a unique cycle type assigned to every permutation, which happens to be an integer partition. So the sign is just -1 to the n minus the length of the partition. And I've listed here from S2 through S7, I believe. And again, I have some stuff blocking the right side of my screen. So, okay, so 1, 1 is less than 2, and the signs are 1 and -1. 1, 1, 1 is less than 2, 1 is less than 3, and the signs are 1, -1, and 1. So it's a sequence of 1s and -1s. And why am I bothering to list these? Well, if you add them all up, oh, why didn't it advance? Let's see. Oh, there. If you add them all up, you get something interesting. So here are the sums in bold. They're all one except for that first one. So this is my first observation, is that this sum is always non-negative. And in fact, it's equal to the number of partitions into distinct odd parts or the number of self-conjugate partitions. I'll say a little bit more about what self-conjugate means a little later. So here, at the bottom here in red, you can see I've listed the number of partitions with distinct odd parts, so you can see why there are so many ones. It grows rather slowly compared to the partition function. I don't know if this is a new observation, but this is something, a very, very special case of what I'm about to talk about. Let's see. So my proof of this used representation theory, and I didn't really think about it at all until I started to think about this talk, this particular result. Okay, so what I really want to look at is the sequence of partial sums in that sequence in reverse Lex order. And here's my conjecture. For every partition, fix a partition mu of n, and then take this -1 to the n minus L of lambda for every partition in the interval from the all ones to the mu. Okay. So let me just go back for a second. Oh, so here, so what am I doing? Like we can just do S5 here. So I have 1 minus 1. So the sequence of the partial sums would be 1 and then 0. You can see my cursor, right? And then it'll be 1, right? And then 2, and then 1, and then 0. And then we're saved because we add a 1, right? So even though you can get to 0, you never actually become negative, right? So here's the sequence of partial sums for S8, S9, and S10. And I've underlined increasing runs for a reason that I will get to later. You can see that you hit a lot of times, you hit 0 a lot of times, but you're always saved. You never get down to -1. Right? Okay. I do not know how to prove this, so this is open.
A quick question.
Yes.
What is S8? Like, what is that just the partition with 8 blocks in one row?
S8 is the symmetric group on 8 letters. Did I not say that somewhere?
You possibly did, but I.
Oh, okay. So what I am listing here, let me go back. I'm listing all the partitions of 8. Maybe I didn't say that.
Okay. So this is just all partitions of 8. We're not cutting it off anywhere. Yes.
No, this is all of them. So
okay.
There should be P of 8 partitions here, which is what, 15, right? There should be 15 numbers in this row and 22 in the next one, right?
Okay, I'm caught up.
Yeah, good. Thank you. Okay, so a very quick crash summary on the parts of representation theory that I need for this talk, right? Everything is over the complex field. So what is it? All my groups are finite. A representation of a finite group is just a group homomorphism from the group G to GL of V. V is a complex vector space. GL of V you should just think of as invertible M by M matrices if the dimension of your vector space is M. Okay. The dimension of the representation is, by definition, I'm making a definition here, is the dimension of the vector space. And the character of the representation is the trace. So if you're not used to thinking about characters, remember phi of G is a matrix, an invertible matrix, and I'm just taking the trace and that's the character, right? So in particular, the dimension of the representation is actually the value of the character at 1, I'm writing 1 for the identity element of the group, right? Because this is a dimension V by dimension V matrix. So it sends the identity element of the group to the identity matrix. Okay, so, these are facts that you can find in any book, baby book on representation theory. The character, chi-phi, determines the representation up to isomorphism. It's constant on conjugacy classes. It's what's called a class function. So you can see this is simply a consequence of, similar matrices have the same trace. That's all we're saying here. We say the character is irreducible if the vector space has no proper G-invariant subspaces, right? The really important things for this talk are that the irreducible characters correspond to conjugacy classes, and any character can be uniquely written as a non-negative integer combination of irreducible characters. So those are the two things. And the thing that I'm going to be looking at a lot is the character table of a finite group. So that's a square matrix. And the way I'm going to write my character tables, the rows will be indexed by the irreducible characters, and the columns will be indexed by the conjugacy classes. And since there's the same number of each, I have a square matrix. The ij entry is then the value of the character indexed by the row on the conjugacy class indexed by the column. Okay. Is there any questions about this? Okay. All right. And then I also want to say something, again, I will be brief here, about partitions and symmetric functions. Partitions we've already talked about. So the third item here, P subscript R is the rth power some symmetric function. So it's a symmetric function in an infinite number of variables. It's x1 to the r plus x2 to the r and so on. You can extend it multiplicatively to a partition, P subscript lambda, and you're just multiplying P of the lambda i's of the parts, right? S lambda is the short function indexed by the partition lambda. I'm not going to define it, but I am going to tell you how I use it. So the connection to the representation theory is you should think of P lambda as another way of describing the class function that's 1 on the conjugacy class indexed by lambda and 0 elsewhere. All this, by the way, pertains only to the symmetric group Sn. Okay? And you should think of S lambda as coding for the irreducible representation of Sn indexed by lambda, right? And if you know all this stuff, then great. All right, okay, so the particular representation that I'm interested in here is what I call the conjugacy action. So any group acts on itself by conjugation. In Lie algebras, this is the adjoint action, right? So what does conjugation do? It just, it moves the elements of the group around. But as we know from, like basic algebra, in the symmetric group, for instance, it definitely preserves the conjugacy classes. So conjugacy classes in any group are invariant under this action. Okay, so there's this big theorem of Lou Solomon from 1961 that tells you exactly what the multiplicity of an irreducible is in this conjugacy action. And I say big theorem with a smile because it's a one-page proceedings paper back in the day when they used to write one-page papers. So what does it say? It says the multiplicity of the irreducible chi is the sum over all the conjugacy classes of the character value on that conjugacy class, right? And then the second fact, I'm just putting it in here because I I was just very surprised when I was doing this work to find that this dates back to 1947. It is not frequently referenced at all. This is James Sutherland Frame. I just have to write out his name. It's the frame as in Frame Robinson Thrall, the hook length formula, if you know it, right? He had actually computed 14 years before Solomon, he had computed the character of this representation, the conjugacy action on a finite group. And it has this expression, right? It's chi times chi bar. Chi bar is complex conjugation, the sum running over all the irreducibles. Anyway, but it's Solomon's result that I'm going to be interested in. So if you think about conjugation, you can see that the character value on a conjugacy class is actually the order of the group divided by the order of the conjugacy class, because, well, the character is the trace of G. So you're counting what points are fixed under conjugating by the group element G, and you're just counting the centralizer of G, right? So actually, the reason Solomon's paper is only one page is because if you combine this fact with the orthogonality relations for characters, it is literally a one-page calculation. Both those things are actually. Okay, so again, for the symmetric group, conjugacy classes correspond to partitions of n. So we can express both of these results in terms of symmetric functions. This is in Richard Stanley's EC2. Whoops, sorry. You can write the Frobenius characteristic. So this is really Solomon's theorem written in terms of the Frobenius characteristic. It's the sum of all the power sums p lambda, each taken exactly once. And you can write Frame's result this way, that it's the sum of a Schur function, internal product, if you know what that is, with itself. It just corresponds to tensoring representations. Again, the sum ranging over each, you take one for each partition. Okay, but again, it's this first fact that I want to focus on. And I just, sorry, I'm just checking to, oh, I did it again. I always forget to set my timer. So, all right, never mind. I'm sure you will tell me. Can someone just give me like a 5-minute warning or something? I would appreciate it. All right,
Sure.
great. Okay. All right, so I want to restate Solomon's theorem in terms of the character table. It simply says that the row sums in the character table of a finite group are non-negative integers, because what Solomon's theorem actually said was, if you take the row sum corresponding to chi, so let me maybe go back. Yeah, right here, this. What is this? This is just, you're looking at the row indexed by the character chi and taking the sum of all the entries in the character table, right? Okay, so here's some examples for Sn. So this should, I hope, make it more concrete. So the columns are indexed by the conjugacy classes. The rows are indexed by the characters, but they're both indexed by partitions of n, right? You're just looking at integer partitions of n. So for S2, it's 2 and 1 squared. If you look at the row sums, you see that you get 2 and 0. By the way, the top row, the way I'm writing my my character table, I'm ordering them in the partitions in reverse Lex order. So my top row is going to correspond to the trivial character. In the top row, the entries you'll see will always be all ones. In the bottom row, the entries you'll see will be the -1 to the n minus the length of the partition. This is the sign character of Sn, as it turns out. All right, so you'll always see a sequence of -1s and 1s. In addition, this last column will always have positive integers, because if you remember, the value of a character on the trivial conjugacy class, the conjugacy class of the identity element in the group, is the dimension, right? So what we're doing here is just listing dimensions. Okay. All right, so you can see that Solomon's theorem is certainly verified. So the question I want to talk about is the following. If I restrict my row sums to certain columns of the character table, when will I get non-negative row sums, right? So in other words, when will I get an actual representation? That's the representation theory part. That's the equivalent question. The equivalent question to this, to getting non-negative row sums, is saying, when is this multiplicity-free sum of power sums actually sure positive, right? Any questions about this? I have lots of examples, so you'll be able to, you'll have a chance to think about it. All right, so some simple observations. If my subset doesn't contain the all ones partition, that was the last column in my character table, then I'd have no hope of this being a true module, because that's the column that contributes to the dimension, right? So when I'm doing this investigation, I do need to throw the all ones partition into my set. If I only have the all ones partition, I get what's called the regular representation. Then it's just P1 to the n. It's x1 plus x2 plus whatever, raised to that whole sum, raised to the power n. That is well known to be the regular representation of Sn. I mean, if you remember, Robinson-Shenstead, it decomposes that sum into f lambda times s lambda, all that stuff. That's the regular representation. Another thing that maybe if you haven't thought about this, it might be fun to think about right now, is if I only took two columns, so one of them has to be the all ones partition, and the other one you can take any partition you want, then you will always get a representation. It's probably not a very interesting representation most of the time, but why is that? Well, if I take the row sum, so I'm taking the row sum, the value of any character, so fix any particular row, the value of the character on the all ones partition is just the dimension. The value of the character on the conjugacy class indexed by mu, well, what is that? It's the trace of the matrix corresponding to an element with cycle type mu. But this is an element of a finite group, so it has finite order. That means the matrix has finite order. That means the eigenvalues of the matrix have to be roots of unity. So if you're adding up roots of unity, well, you can't get absolute value more than the dimension, more than the size of your matrix, right? So when you do chi of mu plus chi of 1 to the n, you will never get anything negative, because chi of 1 to the n is a positive integer. Okay, all right. Okay, so here are some examples. Even if I throw in my all ones partition, I don't necessarily get something that's sure positive. You can check this. So I usually check these things in Maple with John Stembridge's SF package, but I'm sure you can do it in Sage. So if you look at the multiplicity of 2, 1 to the 4 here, you will get -1. In this example, you'll get -1 again, but it's for the partition, for the row indexed by the character corresponding to 3, 3. The point is that this is a non-trivial problem. Okay, so here are some results. So this is actually a lot of theorems that I just listed together. They all have, well, most of them have fairly different proofs, and so that part of it is a little annoying. Some of them have very nice uniform proofs. So I'm writing par subscript n for the set of all partitions of n, and do subscript n for the set of all partitions of n with distinct odd parts. The cardinality of this, if you remember, was what was counted by adding the bottom row of the character table, all the ones and minus ones. You always got cardinality. The number you got was the number of distinct odd partitions with distinct odd parts. Anyway.
There's a question
So,
in the chat that I could read
yeah.
out. So
Sure.
can you mention how the question is related to the conjecture you mentioned a while ago about adding sums of signs of partitions? And the question being, I'm assuming the question that you wrote out in the previous slide. And let me know if you need me to read the question again.
Okay. So, yes. So I want non-negative row sums. I started out my talk with a very particular row sum, the bottom row of the character table, the ones with ones and minus ones, this one. Can you see that? I'm moving, yeah. All right,
yeah.
So -1, 1, 1, -1, 1. So I apologize when I listed them way back then. What did I do? I think I listed 1 to the n first. Right? I was aware of that. I just didn't want to. It would have taken me forever to redo my matrices. I have a lot of trouble with /begin align. So yeah. So if you look back in maybe the second or third slide, I guess we can't see it. So let's see, 1, -1, 1, 1, -1. Here. You go back. I can do this. Here we go. 1, -1, 1, 1, -1. That is for n equals 4, right? So in my character table, the 1 to the 4th is the rightmost column, and the 4 is the leftmost column, right? So I don't know if this answers your question, but I started out the talk. Is it okay?
So maybe a follow-up question. I think so. Are you, when you're asking this question, are you fixing a row, and
No.
then so you want it for all rows?
Yes, I want it for all rows. Yes.
Okay.
So when I started out the talk talking only about the bottom row, but now I want that bottom row was a special case of this question for all rows. Yeah, thank you.
Okay.
All right. Yeah, so all rows non-negative. That's what is going to make this an actual SN module. Right? So every row sum is the multiplicity of the irreducible index by that particular row. So that's what I want to be non-negative. Okay. All right. So I have more examples here. These examples are constructed by including the all ones partition and then taking all partitions of n so that n minus L of lambda is odd. And the reason I wanted to do that is because I have a theorem that says when n minus L of lambda is even, I do know that the row sums are non-negative, right? So you can see this example, and now I think there ought to be a way something that tells you what your next slide is. So let me see. Okay. All right, I remembered correctly. Yeah. Okay. So here is in orange, I have highlighted. So I hope this is helpful because it took me forever to do this highlighting. I've highlighted the columns that I'm choosing, right? So C11, C10, C8, C6, C4, C1. The subscripts are now superscripts because I wanted to underline and it was getting all messed up. Anyway, so I'm taking, here's the sum of power sums that I'm taking. Right? And when I expand it into short functions, everything is positive except for that last -4, which I hope you can see. And actually, I cannot see my last column. Can you see my last column? It should have a heading of S for sum. Yeah?
Yes,
Okay.
we can see it.
Okay, great, thank you. So the entries in that last column should be 6, 7, 14, 10, 3, 16, 10, 7, 4, 3, and -1. Okay.
The last one
And-
was -4.
-4, sorry, it should be -4. Okay, so you can, in the bottom row again, -1, -1, 4 -1s, and 5 -1s, and a +1, so it works out to be -4. So this is an example where it fails. You know, I don't get an actual SN module, right? So I'm hoping this example will sort of clear up what I'm doing. Are there any questions here? Okay, is it good? Okay. So again, just maybe one last time, when I look at the, say, the row sum corresponding to 411 here, what I'm actually computing is the multiplicity of the irreducible indexed by 411 in the sum of these conjugacy classes. Okay. All right. So I do need to say something about the orbits of the conjugacy action. These are obviously the conjugacy classes. Conjugation transitively permutes the n cycles, so it's easy to write down what the representation is on the class of n cycles, the long cycle. Whoops. And if you have an arbitrary permutation of type lambda, the conjugacy action is just the trivial representation induced from the centralizer of that element. And what do centralizers look like in the symmetric group? Well, they look like direct products of Riesz products. And if you have Riesz products in the symmetric group, you have plethism in the ring of symmetric functions. So almost all my results are eventually boiled down to computations with plethism. So it looks like this. I'm not going to say a whole lot about this, but this H lambda of F, when you see that, you should think of it as the orbit of the conjugacy action for permutations of cycle type lambda. And that is its own SN module. It's an SN invariant subspace. Okay, so I can restate Solomon's theorem this way in the ring of symmetric functions. When I add up all these orbits, I get, again, a multiplicity-free sum of power sums. So when the reason for doing this is I can investigate multiplicities of irreducibles on the right-hand side by looking at multiplicities of irreducibles on the left-hand side. And another reason for doing this is that I can also generalize it, which I'm about to do. So now, so if I have, say, a cycle type that looks like k cycles of length m, within the cycle, I'm acting by conjugation. So I'm just moving the cycles around, but I can also permute the cycles. In ordinary conjugation action, that is just the trivial action of this SK, but I want to twist it by a sign. So now I want to act like the sign here. Okay, so I'm giving you a very sort of top level intuitive description of this. But if you do that, then you get the Frobenius characteristic that you get looks like this. It looks like a product of EMI plethism with FI. So the point is that instead of the trivial representation, you now have the sign representation here, right? So what does this have to do with the character tables? That's the interesting part. Okay, here's what it has to do with the character table. So it turns out that you can prove that this twisted action is actually the same thing as adding up, as looking at the row sums in the character table, where now you've restricted to columns of partitions with all parts odd. So In particular, because I've constructed a module with this Frobenius characteristic, I now know that this sum is sure positive. I also know, by the way, that it's self-conjugate for reasons that I'll mention a little bit later. But what that means is, if I now look at the row sums for this particular set of columns, I should always get non-negative integers. And here they are. So what am I doing here? Let's see, 2 isn't very interesting, but 3, there are only two of the 3 partitions have all parts odd, 1, 1, 1, and 3. And if you just do the row sum for that, this is what you get. Notice it's symmetric. That's the part that said something about the word self-conjugate. Okay, here's 4 again. Again, there are only 2 partitions that have all parts odd. So the odd row sum is 2, right? And then you have 3, 1, 3, 2. Again, it's symmetric because these partitions pair up in self-conjugate pairs. So what does self-conjugate mean? Well, 3, if you think of the Ferris diagram, 3, 1, and I can't draw, so 3, 1 is 3 rows in the one box and then 1 row in the next one. If you flip that about the main diagonal, you're going to get 2 rows in the first box and then 1 and 1, right? Okay, so a self-conjugate representation has the property that the multiplicity of lambda is the same as the multiplicity of the irreducible indexed by the transpose of lambda. So that's what you're seeing here. Okay, so 4, for instance, its transpose, if you by transpose I mean transposing the Ferris diagram, is 1, 1, 1, 1. Okay. Okay. All right, so here's 5 again. Let's see, so now I'm adding the column of all ones, the column 3, 1, 1, and the column 5. Okay. And you get this. 3, 1, 1 happens to be self-conjugate. If you transpose the Ferris diagram, you get the same thing. So that's the odd man out here. Okay. Same thing for 6, right? Okay, so now I highlighted in pink or whatever all the partitions that have only odd parts. Right? And by the way, you can read off what they are because they're written out. The partitions are written out explicitly in this column that says irrep. Right? So C1 is the top one and C11 is the bottom one, and they're in order. Okay. Okay, let me go back to reverse Lex order. So that was one theorem. So that's one really nice class where we know that the row sums are non-negative. Here's the big conjecture. For any irreducible character of the symmetric group, if you fix a partition of n and you take lambdas from the all ones partition through the partition mu, so this is in reverse Lex order, and you add up the character values, you will always get something non-negative. So I checked this a long time ago, up to n equals 20. Sullivan's theorem is the case when you add up all the partitions, so all the columns. And the conjecture that I meaning the conjecture I started this talk with, is the case when the character is the sign representation. So I hope this clears up. Somebody had a question before. I hope this clears it up, right? So that's why I was listing all those 1s and -1s. Let's see. So, okay, let's just do this here. So if you look at the bottom row, since I'm probably running out of time now, if you look at the bottom row, and you have to start at the last column. So remember, I played this trick on you and reversed my order. So 6 is here and all ones is at last. So I have to start with the all ones partition. And you do the partial sums, 1 minus 1, 1 minus 1. You will always get something non-negative. And you will get that, you can stop anywhere. So before I went all the way down, but you stop anywhere and it's always non-negative. I think it's fair to say that I don't really have a good idea of how to prove this. I have some partial results that were a lot of work to prove. I can prove this if mu is less than or equal to this partition that has one part equal to 3. So if I write my partitions in reverse Lex order as a chain with 1 to the n on the bottom and n on the top, and so I'm moving up the chain. So this is telling me where I can stop. If I stop anywhere up to here and add up the columns, I will get something non-negative. And also, if I go all the way up to n minus 4, 1, 1, 1, 1, and beyond, then I can prove that I get something non-negative. This proof is absolutely horrible and nobody should ever read it. The first proof is actually quite nice. There's some nice things in it. Okay, so I have similar conjecture and same partial results for the twisted conjugacy action. So you can do the same thing with all the parts being odd. What would be really nice is to find, a nice natural module somewhere whose representation is exactly this. All right, so positivity. So positivity as opposed to non-negative negativity. So you may have noticed, if you keep an eye out for such things, that most of those sums, row sums, were actually not just non-negative, but positive. So a long time ago, Avital Frumkin proved, in fact, that indeed for the full conjugacy action, the row sums are indeed strictly positive. So what that's saying is that every irreducible appears in the conjugacy action, as long as n is not equal to 2. And then there were other proofs. Donald Passman, he's a algebraic representation theorist. I mean, he did this in much more generality for other groups. There are these things called global classes. And I have a stronger result for Sn, where I can identify, this is I didn't write it out, but this is an if and only if theorem. I can tell you exactly which conjugacy class has all the irreducibles. So anyway, the row sums for the full conjugacy action are positive. And so I can also tell you when in some of these other cases that I had mentioned before, when the row sums are strictly positive. And these are the cases, like, for example, the nice one where lambda has all parts odd. That's, again, strictly positive. Okay, so open questions 3, I guess I'm up to. I wasn't keeping track. So the first question is there a combinatorial interpretation for the row sums? At least for the full conjugacy action. This is already in EC2 in this exercise, but also for the twisted action, right? So we do have a combinatorial interpretation of sorts for the bottom row, for the sign representation, right? It's either the number of partitions whose parts are distinct and odd, or the number of partitions with all parts odd. I actually don't know if I said this, but it's true. And I proved this using representation theory, but as I was writing this talk, I realized that at least for the sign representation, there's probably some sign reversing involution or something that you can do to get this fact, right? In general, I don't know. I just don't know how to get at a combinatorial interpretation. Maybe use Murnaghan Nakayama. I know Stefan who's on a plane now, I think, has thought about this a lot. Okay, so how much time do I have?
Roughly 10 minutes.
Okay, all right, that's fine. So here's another, whoops, something, I think my mouse or something is very sensitive. Okay, another class of subsets that I can handle, and this is a sort of a completely a different proof technique. So fix a set of primes, and now I want to look at row sums in the character table when I'm restricting to columns indexed by subsets that look like this. It's either partitions where the prime factors of each part are a subset of S, the set of primes that I've picked, or at the other extreme, no prime factor of the part of my partition is in my set of primes. In either of those cases, they're actually complementary in some sense. In either of those cases, I can show that the row sums are going to come out to be positive. And if you're, I know this is a strange thing probably to do if you've never seen it before, but so let me talk about the special case when S consists of a single prime, which is actually what I started with. I actually started with the prime 2. Okay, so in that case, I'm looking at partitions where parts are either a power of Q, my prime Q, or parts that are relatively prime to Q. When Q is 2, I'm simply saying that the parts are all odd, right? So this is the familiar thing that you know. The first one, when Q is 2, says every part is a power of 2, and that is the representation that I get out of that is has some really remarkable properties with connections to all kinds of things in configuration spaces and just lots of different things. But for arbitrary primes bigger than 2, I haven't been able to find anything interesting about this representation other than the fact that it does give you these non-negative row sums in the character table. Anyway, Q equal 2 would be a whole talk by itself. So I'm not going to say any more about that. All right. So what I was trying to do was get like a meta theorem that would tell me, you know, okay, pick this set of columns, you know, and you'll get non-negative row sums guaranteed. It's an if and only if type theorem. I did not succeed, but this is what I was able to manage. I'm defining, so take any non-empty subset of positive integers t with 1 in t, and I'm going to define this function psi superscript t. Right? It's defined like this. It's a sum over all the m's in t that are also divisors of d, and then it's m times mu of d over m. Mu is the number theoretic Möbius function. So if t consists of just 1, the number 1, this is the full number theory. This is all you get is mu of d, the number theoretic Möbius function. If t is all the positive integers, you get the totient function. And if you've worked with these things, this might be ringing, you know, there might be bells going off in your head now. So for the experts, when t is just 1, this fn of t that I've written out here is the Frobenius characteristic of the Lie representation. And when t is all the positive integers, it's the Frobenius characteristic of the conjugacy action on Sn. Right? If you don't know what that means, just ignore what I said. So the theorem is this: if these things are sure positive, and they're not always sure positive. They are in the two cases that I just mentioned. But if they are, then so is this product in the formal power series of symmetric functions, which comes out to be this multiplicity-free sum of power sums. So my hopeful idea was, how can I use this theorem to find more subsets, right? Okay, so here's a conjecture. This symmetric function, and therefore this sum, because of the previous theorem, is sure positive if t is just something very simple. It's just this first k consecutive integers. So I'm looking, in other words, in my columns, I'm looking at columns indexed by partitions where the parts are always less than or equal to k, or if the parts are congruent to 1 mod k, right? So Richard Stanley, again, this was a long time ago when I didn't know how to do a lot of stuff. I know a little bit more now, but he checked this conjecture I checked it for a lot of things, like up to n equals 40 or something. So I do know it's true for k equals 2, because then for k equals 2, again, this case gets back to the odd partitions with odd parts, and then there's n. Yeah, so if you take n here, that's Solomon's theorem all over again. Okay, so I think I already mentioned this. Open question. It would be really nice to find modules associated to these things, right? That would, just finally catching a typo again. You don't know how many times I looked at this. All right. I wanted to say something about dominance order. So I've been focusing on reverse Lex order. You could try other orders on partitions, right? As long as they include that all ones partition. Dominance order fails right away in the first instance where dominance departs from reverse Lex order, right? So if you take the interval from the all ones to 4, 1, 1, you can see, so we've left out the 3, 3, and you get -1 for the row sum, right? So it's very, I don't know how to say it. It's very tight. Okay, do I have time? Now I have to ask how much time I have.
A couple of minutes.
Okay.
Depends on how many minutes you want for questions.
Yes. So I just want to say something about asymptotics, because I know a lot of people are interested in asymptotics, and this is the one asymptotic thing that I ever did in my life. Always like carefully avoided anything to do with analysis. So just because it seems very hard. Okay, so I'm counting. So I'm going the other way now. F of n is the number of subsets of the set of partitions where at least one row sum is negative, right? I do want to throw in, so this is the number of subsets that contain the all ones partition, and you still get a negative row sum. So I worked really hard on the computational aspect of this, so I'm kind of proud of it because I am not good at this stuff. Here are my numbers. So up to actually, Richard had computed f of n up to 7, and he wrote to me and said, well, do you know anything about this? And I said, no, I don't. But then I verified his computations using maple and symmetric functions, if you can believe that. It was a terrible way to do it. It took forever. And then I did 8 that way. But then somebody told me that, oh, Maple has character tables. And here I was looking in the back of James and Kerber and carefully copying down the entries. Probably ruined my eyes. But anyway, yes. So then I used the matrix and the it ran much faster that way because I wasn't doing symmetric function computations. I got up to n equals 9 and it stopped. But by then I had figured out ways to eliminate cases. And my husband finished the computation for n equals 10, which I could never have done by programming it in C. Like he threw out all my code and redid it. And it took a long time. It took, I believe, something like 83 hours or something, but he came up with this impressive number. So you can see the proportion, right? Yes. So I have more, and now I have asymptotics conjectures. Right? So this is my conjecture. It's based on that previous table or on thin air, depending on how sophisticated you are about asymptotics. And so here, you know, there's a, I think it would be nice if they approached a limit. It's some positive limit, right? There's some, I just wanted to mention there's some absolutely charming papers about the probability of sure positivity. In particular, the first one by Rebecca Patrias, I don't know how to say the name, and Steph, where they actually compute probabilities. So if you like that sort of stuff, you know, that's it. Okay, that's really all I wanted to say. I will stop. I have references, and thank you very much again.
Let's thank Sheila. Thank you for the excellent talk.
Thank you.
All right, before questions, I just wanted to say for the recording as well that I lied earlier. We do have a speaker next week. And so that's good news. So come back again next week. And yeah, let's go ahead and open the floor for questions. I think, Marge, do you have a question? Are you raising your hand?
I am, but I think Yannick was first.
Ah, go ahead.
Oh, you can go ahead, and then I will ask.
One of us go. Well, can you go back to one of the matrices?
Yes, sure. Which one?
That's great. So, my general question is how much is the sure positivity of a selection of columns really predicted by the bottom row? So for example, if I just take the columns in which the bottom row has a 1, is that going to give me positives everywhere? Or I guess more generally, given any choice of columns, are the numbers in the rightmost column all greater than or equal to the one for the sign representation?
So the rightmost column is the dimension. And that's always going to be, all the other character values are going to be bounded by that in absolute value because of that eigenvalue argument that I mentioned.
Right. But no, I don't mean absolute value. So again, I'm thinking to what extent knowing that you get a positive row sum in the bottom row tell you about the having positive row sums in the other rows?
Right. So the short answer to your question is I do not know, but what is interesting about your question is that when I did all those asymptotic computations, I did actually use something about how the sign representation worked. But I had an example initially, I believe, where this one, yes. Right. So here, so I'm not telling you what the multiplicity of the sign representation is, but you have other things that fail. I think I have to look. Let me see. I don't know. The answer to your question is I don't know. but let me see. Oh, forgot. I have to look at 6. Sorry. Yeah. 3, 6. So here, so in these examples, the only one that fails is the sign, right? All the others are positive. But there are, I believe, there are some where the sign doesn't fail and the others do, but I don't see one right now, but
Okay.
I'll get back to you on that.
I see one right now.
I'm sorry, yes.
I was able to, so if you look at the 3 squared row,
Yes.
and you look at all of where there are negative entries, I believe it adds up to -6.
Mhm.
And so if you take those and the last column, that will fail. But I believe if you look at the signed representation, it won't.
Okay, that's what I was going to say, but I just couldn't remember. Thank you very much, Mark. Yeah.
But there's still, I guess, my sub question is if you just take the columns that have 1s in the sign representation, I think your example, Mark, wasn't that. But anyway.
It wasn't, no.
Yeah. Wait, so this is when n minus L of lambda is, this is all the even permutations, right? That's what this is. So I think that was one of my theorems. I'm trying to remember here. Yes. So in that case, it's a theorem. That
Okay, that's the one there. Okay.
Okay. Yeah, right. Am I doing this? Yeah, that one. Yeah. Okay. All right. Yes. And someone else had a question.
Yeah, go ahead, Yannick.
Yes, thank you very much for your really nice talk. I have a lot of questions, but I will try to be very explicit. So I have 2 questions and 2 remarks. My first question is about at the end of your slides for the asymptotic part. The Fn.
Yes, this?
Yes, so for the partition function, the generating function of the partition function can be written as a product of
Yes.
one. Is there something like this for the generating function of f of n?
I have no idea. I haven't thought about it at all. Yeah.
Okay.
Yeah,
Okay.
I don't
So
know.
that's my first question. My second question is there is a Hopf algebraic analogy from the Hopf algebra of symmetric function to the Hopf algebra of quasi-symmetric function, where you have analog of short function and analog of power sum. Have you tried to see about your conjecture on the sum of power sum? Have you tried to see an analog result on quasi-symmetric functions?
No, I haven't. I haven't thought about it at all. That's a great idea.
Okay. Okay, so that's my 2 questions. Thank you. And I have just 2 remarks. My first remark is that there is a paper of Sarah Bealey from 2 years ago, I think, where she defined 2 new posets on Young diagrams, which are analogs, in fact, of the Wick-Bruhat order for permutations. So I don't know if you're aware of this one. Maybe it can be interesting to try to do what you did with the classical partial order on Ferrer diagrams.
Yeah, no, I don't know.
I can. So this is the link. I can put it on the chat of the paper with Joshua Swanson and 2 other co-authors. So these 2 partial orders are not very well known because it's very recent, but maybe it can be interesting to also do the analog calculation that you did with the standard partial order. And my last remark, I don't know if it is related to your talk, but so for the character tables of the symmetric groups, is there something known about the sum of all the elements in the matrix? So looking at your examples, it always give prime numbers. So is this true in general?
I don't know, but I think something about what you're saying rings a bell. Maybe a paper of Christina Bessenrold and Jan Olsson.
Okay.
You might want to look. I don't know, but I have a very vague memory of something.
Okay. So just to make an example, the character table for X5 or X6, the biggest one, yeah, that the other one sum 89. So this one sum of 8.
So if you add all, you're adding all the entries.
Oh yeah. So I'm just adding the yes, all the elements.
Mm-hmm.
This one add a prime number, and the last one add 89, which is also a prime number.
Which is also
a prime number. So
okay.
This one add 89. So
Okay.
it's quite miraculous. But I don't know if this is well known or not.
Yeah. Okay, I don't know. Yeah.
Okay, thank you very much.
Yeah, thank you.
We have also a question by Xinjie Liao.
Yes.
Yes. So I want to ask. So the symmetric function you consider is like the sum of p lambda, where lambda is over like some restriction on all the partitions, right? Have you looked at like instead of partition, you look like compositions instead? Like sum over like all the compositions, or maybe like restrictions?
No, I haven't. So then you would get, it wouldn't be a multiplicity free sum anymore, right?
I mean, because I remember like if you just look at all the compositions, it's the Frobenius character of the toric variety of associated to the permutohedron, or it's also like the sum of all the Eulerian quasi-symmetric function defined by Michel Fox.
Yeah. No, I haven't. I mean, that would be a good thing to do, I guess. Composition. Yeah, sorry to write this down before I forget it. Okay. Thank you.
Yeah.
All right, let's thank Sheila real quick, and if she has time, we can hang out a little bit and talk further. But thanks again, Sheila. That was excellent.
Thank you. Thank you very much. Should I stop sharing, maybe?
You may.
Yeah.
So I did have one question, because you introduced this RevLex order, and I'm wondering where that name comes from, because I feel like if I was to name that, like, that doesn't feel like it's RevLex to me. Like,
Okay, so I've been trained in some sense from mathematical birth using the first edition of MacDonald.
Okay.
I think that's what he called it. I don't know what the origin of it is.
Sure.
So yeah, I don't know. It's funny because I was just looking at my first edition of MacDonald, and I realized I sort of literally jumped out of my seat. He never once mentions the word Schur functions. He calls them S functions. And I don't think all these years that I've been looking at it, I even noticed that.